Awesome. Go.
Hi, everyone. We're back with the MLSys seminar. Today, we're super excited to have Tim Dettmers as the guest speaker. We're co-hosting this along with CS229S, the Systems for Machine Learning course at Stanford. Dan is here.
Hello, everyone.
And I'm Simran. We'll start with a brief intro to Tim, and then he'll take it away. So Tim is a graduating PhD student at the University of Washington in Seattle, and he's advised by Luke Zettelmoyer. His primary research goal is to democratize foundation models by making them more efficient and accessible through quantization, sparsification, and building machine learning systems that use consumer-grade hardware. So for those of you watching from CS229S, touching on topics from the last few lectures. He also constructs a lot of educational materials and open source tools, for instance, the Bits and Bytes library and some of the blog posts that he hosts on his website. We're super excited for his talk. And with that, Tim, take it away.
Thank you so much, Simran. Let me share my slides. Here we go. So today we talk about how we can democratize foundation models with k-bit quantization. And so the main goal of my research is to democratize foundation models. And one big thing that we can do is that if we have the existing pre-trained foundation model, we can quantize it to compress the memory footprint and make it more accessible so you can use it with less hardware. In this lecture, I focus on QLoRA. QLoRA is a fine-tuning technique. So if you want to customize or personalize a pre-trained language model, you can fine-tune it with QLoRA with a much smaller memory footprint. For example, if you have a Llama 2 model with 70 billion parameters, then you need 23 consumer GPUs. But with QLoRA, you would only need 2 consumer GPUs. And so the costs are much, much lower to fine-tune. With QLoRA, we can still maintain 16-bit performance. And that will be the main thing that we talk about in this lecture, how to achieve that. These are the papers that I will talk about in this lecture. Focus will be on QLoRA, but then also k-bit inference scaling laws and some other background. And let's dive into that. So first, we talk a little bit about background. The more general thing is what is quantization? So if you look sort of in very general, if you have an analog signal and we want to digitalize it, we use quantization to basically bin this continuous signal into some bins, like in a computer, where we have particular bits of information. In general, in computer science, quantization is also if you have a high bit representation, for example, 32-bit float, we want to quantize it to something smaller, like a 4-bit integer. And so what we actually have in this plot is a representation of 4-bit quantization. It's also a histogram. And so in red, we have the normal distribution. And in blue, we have the histogram. And so if you want to quantize the normal distribution to a 4-bit data type, 4-bit integer, then we have 16 different values. And to find these 16 different values, what we do is we look at the minimum and maximum range of the normal distribution. And then we slice it up into 16 different pieces with equal width. And then we take all the values that are contained in each of these bins, in each of these intervals, and quantize it to the middle value of the interval. And if we do that, we reduce the entire normal distribution to 16 different values. And with that, we have our 4-bit quantization. And of course, we can do this with sort of other distributions. So if you have an arbitrary input tensor, you can use the same procedure to quantize it to a 4-bit integer. In my research, I use also different data types and I also develop custom data types that are sort of optimal for neural networks. And for that, it makes sense to try to generalize the perspective of data types a little bit further. So one perspective that I use that's quite useful is I see a data type as a mapping. So we have, for example, for 4-bit data types, you have 16 different values. We can describe it as a mapping from these 16 different indices to a particular floating point value. And the problem is different data types have different ranges. So if we want to have sort of a general scheme of how to represent all data types, what we can do is normalize it into the range -1 and 1. And that looks like this. So we have an int4 data type and a floating point 4 data type. And now they're in the same range, and they map basically from a sequence from 0 to 15 to these floating point numbers. And so that is how we can represent a data type. Now, if we want to do a quantization, we can follow a two-step procedure to do the quantization of an input tensor. So if we have the input tensor X and we want to quantize it with a certain data type, the first thing that we do is we normalize it into the range -1, 1 to have the same range as the data type. We can do that by dividing by the absolute maximum value of the input tensor. Once we have done that, they're in the same range, and now we can quantize by finding the closest value of each of the elements in the tensor to the data type values that we have. And if you have integer, you can just use rounding. That will get you to the closest sort of integer value. But in general, we would need to do a binary search. Just to make this a little bit clearer and also show how general this is, here's an example of a non-standard 2-bit quantization. And so we have a 2-bit quantization, 2-bit data type that maps the indices 0, 1, 2, 3 to the values -1, 0.3, 0.5, and 1.0. And so what we see here with this data type, it's a little bit weird. It only has one negative value. And then we have the input tensor 10 - 3, 5, 4. And so if we want to quantize this input tensor, we go through the steps that I outlined before. So first, we want to normalize the tensor into the same range. We do that by finding the absolute maximum value, which is 10, and then dividing all the input values of the tensor by 10. Now we have the same range. Now we do the binary search to find the closest value for each input tensor element to the data type. Once we have found that, we can convert these values to their index values. And this is how we store a data type. So we just store the indices of the data type. If you want to dequantize the data type, we take the indices, do a lookup on the values, and then we denormalize by multiplying by the absolute maximum value, which was 10. So we need to store both the indices and this quantization scaling constant, the absolute maximum value. And so with this procedure, we can quantize and dequantize, and so change between data types with higher and lower precision. But what you see here is that if you compare the input tensor and the output tensor, we made one big error. The -3 turned into a 3. This is because our data type only had one negative value, and it was not very well suited for this quantization. And that is also an important part of my work. If you quantize neural networks in low bit precision, important thing is to think about how do you design a data type that is good for your problem. And for different problems, you need different data types because each data type has sort of advantages and disadvantages. Just to give you an example, here this is dynamic exponent quantization. That's a quantization that I developed for optimizer states. So if you have the atom optimizer, you have a ratio of optimizer states that is used stochastic gradient descent. And so with this ratio, and if your denominator is very large or very small, you can have extremely large values or extremely small values. So you need to represent a very wide range. But then also if the denominator and numerator are approximately equal, you have relatively large magnitude values that need to be very precise. And so for that, you need a lot of fraction bits. And so if you have standard floating point numbers, usually you need to decide before you do the computation, how many exponent bits do you have? How many fraction bits do you have? And so what I thought about is like, can we design a data type where this is dynamic? So the exponent, the number of exponent bits and fraction bits are determined at runtime. And so this is what the data type looks like. We have one bit for the sign. Then the first 0 bits are the exponent to the minus 10 to the power of the number of bits. Then we have an indicator bit, which is the first bit that is a 1. This indicator bit doesn't do anything except to indicate that all following bits are for the fraction. So in this case, we have 4 bits for the fraction. And the nice thing about this data type is, as we sort of slide the indicator bit from left to right, we can determine how many exponent bits we use and how many fraction bits we use. And so this makes this data type particularly well suited for approximating a ratio, if you want to quantize a ratio. And this is sort of how you think about designing data types. You think about what values are important and what things do you need to consider, then try to design around it. If we go further in the background, we need to talk about outliers. Outliers are very important in foundation models and neural networks. If you look at other sciences, for example, engineering or also physics, is if some people see an outlier, they say like, oh, this is a measurement error, let's discard it. It's not part of our model. And you can't do this with neural networks. Neural networks, what we have is we often have some normal distributions and then some outliers somewhere around it. But these outliers are so important. If you remove them or have a poor quantization precision for these values, then your neural network will degrade in quality a lot. And so we need to make sure that outliers are quantized well. But then there's also the problem, the outliers can affect the quantization a lot too. So here we have, again, similar example. We have a 4-bit quantization, but now I inserted an outlier at -10. And so we normalize into this range, slice the distribution into 16 pieces with equal width. And this is our quantization. What we find is between -10 and -3, all the quantization bins are empty. And so only 8 quantization bins are filled with values. And that makes this quantization basically equal to 3-bit quantization. So the quantization error that we're getting from this quantization with 1 outlier is the same as the entire normal distribution with 3 bits. And so we lose 1 bit of information. And so that can be quite severe and degrade performance quite a lot. And so we can get around this by using something called blockwise quantization, or often also called groupwise quantization. And so what we do is we take the input tensor, and now we slice it into tiny blocks. And all these blocks are independent. We quantize them independently. And so if a couple of outliers exist in the tensor, they will be confined just to this block. For example, in the upper left, that would be equivalent to a 3-bit quantization. But all the others are basically unaffected by this 1 outlier in a different block because the blocks are independent. And so with that, on average, we get much higher quantization precision at a small overhead of an additional absolute maximum normalization constant for each block. And so blockwise quantization is very important to get stability by confining outliers to blocks. Okay, we have 1 more concept to go before we dive into QLoRA. And so this is a bit more complicated. This is a plot from K-bit inference scaling laws. And so this work is mainly about the question, how can we maximize the information density per bit? So for example, if we have a 10 billion parameter foundation model in 8-bit, or a 20 billion parameter model in 4-bit, they have overall the same amount of bits, 80 billion bits. But one of these models will have higher performance than the other. That means the information density per bit or accuracy per bit will be better for one of these models. The question is, what precision do we need to use to maximize the density per bit? And so this plot gives us the answer. In this sort of paper, I ran 35,000 experiments across 31 foundation models. This is just OPT, sort of a little bit older now foundation model, but it has a lot of different scales of these models. And so in this plot on the x-axis, we see the total number of bits in the model. And on the y-axis, we have mean zero-shot accuracy. So we prompt the model across 4 different tasks with a question, and it gives us an answer. Then we score the answer, how accurate it is on average. And so in colors, we have 16-bit, 8-bit, and then 4-bit. And we see 4-bit is at the top, and it gives us the highest information density. Per bit, we get the highest mean zero-shot accuracy. But at 3-bit, we see that accuracy drops, information density drops. And it's also jagged, which often indicates instabilities. And so from this plot, we see that 4 bits seems to yield the highest information density. And from all these experiments that I ran, if you just have the information in the weights, it's very difficult to do better than 4-bit if you want to increase information density. You can do better if you both consider the weights and the inputs, but that's a more difficult problem. Beyond this, so now we know basically you should use 4 bits and as many parameters as possible to increase the information density if you want to fit it into a certain memory footprint. But there are a couple of other factors that are important. And so again, we have the same plot here with information density, but now we look at block size. So again, block size is used to confine outliers into smaller blocks. But then it's a question, how large do you make these blocks? And what we find is that if you have a block size of 64, a very small block size, the information density increases. The performance gains look a little bit small here, but they are quite significant, particularly if you go lower to 3-bit or 4-bit. But we also have to consider another thing here. If you have a block, each block has its own constant, its scaling constant for the quantization. But if this constant is 32 bits and your block size is 64, that means on average you add 0.5 bits per parameter. So the blue line in this plot is actually a 4.5-bit quantization. It still yields the highest information density though. And so this means that we want to use smaller block sizes. And then we have one last plot in the K-bit inference scaling laws. And this is about data types. So I presented the dynamic exponent that's good for ratios. And then also, if you have integer data types, these lines give low information density. So if you want to increase information density, you should use a floating point data type or quantization, which is an information theoretically optimal data type. Across all models, if you look at it across all models, this is like one example and the Pythia model. But if you look at all models, then actually the information theoretical optimal data type gives us the highest information density if you want to do quantize a model. And so this is the background. Now I dive into QLoRA. And just to give you, again, a little bit of motivation here, if you just have a couple of GPUs lying around, and you want to instruction fine-tune a model. For example, you want to take a Llama 2 model, and let's say you want to build a chatbot for biomedical data. You usually only need to train for a day or fine-tune for a day. But if you use traditional fine-tuning, you will need 23 consumer-grade GPUs to fine-tune. And with QLoRA, we reduce this just to a single GPU if you have a 33 billion parameter model. So fine-tuning doesn't cost much compute, but a lot of memory. And with QLoRA, we reduce this memory so that basically everybody can use these very large models. Large models usually have sort of different properties. They are just much higher performance, much more general knowledge, much more useful. And so that's another thing that we want to do is that we not only want to be memory efficient, we want to preserve the quality. And that's also what we do with QLoRA. And so to give you a little bit more background, why is fine-tuning so expensive? There's one part that is determined by how large is your batch size, but the other part is mostly determined by parameters, and that's actually the most expensive thing if you want to fine-tune a foundation model. So if we go through it, and the weight is usually 16-bit or 2 bytes, the weight gradient is also 2 bytes. Then the optimizer state is 8 byte per parameter if you use Atom. And that is a total of 12 bytes per parameter. And so if you have 70 billion parameters, that's 840 gigabytes of GPU memory. It's like 18 low-grade data center GPUs or 34 consumer GPUs. And so you can improve on that with low-rank adapters. That's a very efficient technique where you freeze the main transformer, and now you put some tiny layers on top that you fine-tune. And so that makes the gradients much smaller, and the optimizer stage much smaller. You add a couple of weights through the adapters, but now if you tally up all the bits, then the majority is in the weights, 16 bits. But overall, we only have 17.6 bits, or about 17.6 bits per parameter. And so if you have a 70 billion model, that gives you 150 gigabytes of GPU memory. So now we are down to 4 data center GPUs or 8 consumer GPUs. But if you have a consumer machine, it usually doesn't fit 8 GPUs. The maximum that you currently fit with the very large GPUs is about 3 GPUs. So we actually need to use multiple computers to fine-tune this on a consumer setup. So still very expensive. And so you already see where it's going here. Their largest footprint is now the weights. Can we reduce this further? And that's exactly what we do. So we take a transformer model, a pre-trained transformer model, quantize it to 4-bit. Then we freeze this 4-bit model, put adapters on top of it. And so during fine-tuning, we backpropagate through the frozen model into the adapters. And we optimize the adapters to then do the fine-tuning. And that yields a total bit footprint of 5.2 bits per parameter. And that goes to 46 gigabytes of GPU memory. That's then a single data center GPU or 2 consumer GPUs. So now, previously, you would have needed hardware that costs more than $250,000 to fine tune. Now you can do it on a setup that costs only $3,000. So much, much cheaper, very memory efficient. And so this is what we can achieve with QLoRA. And the next thing I will go into is how does actually QLoRA work? I have one slide that I forgot about. You can actually do a little bit better still. So this is Alyssa Advanced. She combined QLoRA with flash attention and 8-bit optimizers. And if you use all these things together, you can actually fine-tune a 70 billion model with a context length of 4,000 on a consumer setup. And she noted that this is actually equally powerful to the largest model that Google had just a year ago. So now on your personal desktop, you can fine-tune these very powerful models with QLoRA that were only available in industry a year ago. So very fast progress and very cheap. This is very accessible. Okay, let's dive into how QLoRA works. So it has 3 major components. The first one is a little bit elusive because you don't recognize it so much. It works in a hidden way in the background. And this is a paging system between the CPU and GPU for optimizer states to prevent memory spikes. And so the main problem is if you start a fine-tuning run, you don't necessarily know if it will complete with an out-of-memory error or not. And this is because the memory is determined by the longest document that you fine-tune on. But often, because there's so much data and everything's pre-processed on the fly, you don't know how long is your longest document. And so you will not know if a training run will complete, and because you might run out of memory. And so with page optimizers, we basically designed it to prevent memory spikes. And how it works is similar to the paging system between the CPU memory and your disk. But now we page basically from the GPU. So how it works is if you encounter a long document and you would run out of memory, then the system evicts some pages from the GPU, transfers it to the CPU. Then new memory is freed. It can be used for what it's needed at the moment. And then if we need to do an update on the optimizers, they are transferred again from the CPU to the GPU, and the update can be made. And so with that, we have guarantees. If your fine tuning run starts, it will complete. It will not run out of memory. And this gives much more convenience, and you can prevent memory spikes if you have a couple of long documents. Then the second component is to save a little bit more memory. It's a little bit silly idea. We do a quantization of the quantization, sort of Inception style. And so the thing is, if we do one quantization, we have two parts. One part is the quantized weights. The other part is the absolute maximum constants. And so these can take up 0.5 bits. And what we can do is we can take those constants, just quantize them again. And if we do that, we can compress them to 0.125 bits. So we save almost 0.4 bits. And that might not sound like a much, but 0.54 bits for 70 billion parameters, that's multiple gigabytes. So this quantization is important to fit everything into these smaller GPUs. It saves a couple of gigabytes. And then sort of the centerpiece, we develop a new data type. So this is a data type that's information theoretically optimal for normally distributed weights. So most weights in a neural network are normally distributed. And so with this data type, we find something that is information theoretically optimal. And there's a simple visualization. So in the beginning, I showed you the normal distribution sliced up with equal width bins. And so we get an information theoretically optimal binning if each bin has equal area, not equal width, but equal area. So equal width was the integer quantization. Equal area is the normal float quantization. And so how to interpret this is that if you have a stream of numbers from the normal distribution, then if a number comes, it's impossible to predict better than chance where this number will end up in which bin, because each bin is equally likely. It has the same probability to be basically quantized into each bin. And that makes it information theoretically optimal. And so how you construct it is through quantiles or the z-scores. And then we normalize these z-scores into the range -1, 1. And that gives us a normal float data type. And so these are the three pieces for QLoRA. And now we look at results. So we basically do two things. First, we verify that everything that we build is actually useful and can help us. And then once we have that, we have such an efficient setup that we can very efficiently explore instruction fine-tuning. So to create chatbots like ChatGPT, we can sort of think about the question like, what is the most important thing if you want to do that? What gives you success if you want to do that? And so first we look at 4-bit normal float. Here we see, again, a k-bit inference scaling law plot. And what we find is that the information density for float in blue is lower than normal float in orange and green. And green is also with double quantization. We see double quantization also works. It's a little bit better information density, but we save more memory. So we can actually compress larger models into smaller GPUs. On the right, we have a table where we average across many different models. On the left, it's just llama. On the right, it's many different models. We average all the complexities. And there we see if we go from integer to float, we have an improvement in information density. If we go from float to normal float, we have almost the same improvement in the information density. So a pretty big improvement. And so this shows that the normal float works. Then the question is, does it also work in practice? If we do instruction fine-tuning. This is a little bit messy. I didn't have enough time to clean this up. This is a table of results of llama models that are fine-tuned on 2 different data sets, Alpaca and Flan version 2. The important part is just to look at the mean. That's the mean accuracy on the MMOU benchmark. And if we instruction fine-tune all these models. And then in the rows we have, in the first row, 16-bit. So that's our target, our baseline. And then 4-bit floating point has a lower mean. And then the normal float with double quantization, basically we have the same mean. And that means that our 4-bit quantized model, if instruction fine-tuned, gets the same accuracy as the 16-bit model. So we replicate 16-bit performance. And we also have further results on the paper. This seems to be very robust. So now we have this very efficient system. We have a system that's 4-bit and very compressed, but it can also replicate 16-bit performance. It uses 17 times less GPUs. So now we can do 17 times more experiments to figure things out. And one thing that we did in the beginning is to figure out which data sets give you an advantage. Once we know that, we can dig deeper and figure out what makes these data sets important. And so this is a table of 4 different llama sizes: 7 billion, 13 billion, 33, and 65 billion. And then we have different data sets that we instruction fine tune on. And so one main takeaway that we see is that the FLAN version 2 data set is really good for instruction fine tuning on this data set. The MMLU data set is about reasoning, education, all kinds of general knowledge, and also some specific knowledge. And what we see is that FLAN version 2 gets much higher average accuracy than other data sets. And it's the only data set that still improves the baseline performance at 65 billion scale. So FLAN version 2 seems to be really good, but actually what we found out later is it's a really bad data set for chatbot models. So really good for this data set, but bad for chatbot models. And before I dig into that, let me talk a little bit about chatbot evaluation. So chatbot evaluation is very difficult. Just to give you sort of a taste of it, if you have the prompt, what are 10 tips that make me more productive? That's a very general question, and you can generate 10 tips, but how do you decide which tips are better than others? How do you decide which response is better? For example, it can also be super subjective that some people just want 10 bullet points, give me something quick. And other people say like, hey, I want to have a cohesive argument that builds on top of all these points and makes each point stronger. And so if you give these prompts to chatbots, so for example, 2 chatbots, and then you give humans these 2 responses, and you ask humans, which one of these is better? Then we see actually a lot of noise because preferences differ. When we use GPT-4 for evaluation, so we have a prompt, we give it to 2 chatbots. The 2 chatbots generate a response. Then we give the responses to GPT-4 to say, hey, GPT-4, which one of these is a better response? Then we get less variance, a little more bias in a certain way. But what we also find, it's pretty closely corresponding to how humans evaluate chatbots. So we can actually use GPT-4 to do sort of a sheep evaluation. We evaluate under the Kunya dataset. It only contains 40 prompts. And so we get some results, but please take these with a grain of salt. We compare against ChatGPT and get good numbers, but it doesn't mean that our models are as good as ChatGPT. Because the data set is so small, we don't evaluate on a very sort of general set of tasks. But yeah, that being said, about sort of chatbot evaluation, we need to be careful, but we have a setup with which we can sort of approximate how good are chatbots. And so we have 2 setups, one a tournament style setup where basically 2 chatbots compete for a prompt to generate the best response. Then the judges are either GPT-4 or humans. And then for each game in this tournament, they get points, ELO points, or they lose ELO points if they lose. And if we tally all these up, we get the table on the right, and we see GPT-4 is really good. But we developed the Gunako chatbot, which is based on the Open Assistant dataset. And it performs really well compared to other models, like, for example, Google Bot and also ChatGPT. On the left, we have a more detailed analysis. And again, lots of numbers. The important number is the win rate, the mean win rate compared to ChatGPT in the mean column. And what we see that is that the Gunako chatbot, compared to its memory footprint, is actually very well performing, close to ChatGPT, but extremely small. So you can actually use it on consumer setups. The smallest Gunaco model you can almost use on the phone. So we are very close to sort of using very effective chatbots on the phone. And yeah, the other interesting thing is if you look at the FLAN version 2 results for each category in terms of size of the model, FLAN version 2 is the worst performing data set, often by a pretty large gap. So it's a pretty bad data set for chatbots, but a pretty good set for this other task. And so that's very interesting. So it matters what data you have. The other thing is FLAN version 2 has 1 million different samples. So it's a very large data set, very broad data set. The Open Assistant data set that we're using for Gunaco, we filtered down to just 10,000 data points. So 10,000 data points gives you much, much better performance than 1 million because we pick high quality data points. And so that's also one main insight. If you want to build a high quality chatbot, it doesn't matter how much data you have. The most important thing is that you have high quality data to get good performance. And yeah, a little bit more benchmarks. Here's again the Gunaco data set on a more broad sort of evaluation. And if you control for the memory footprint, it's actually one of the best performing models. So Gunaco 65 billion does pretty well, but it actually is a 4-bit model while all the others are 16-bit models. So it's actually more closer to a 13 billion parameter model rather than the 65 billion in memory size. And if you want to try our model, the Gunaco model, you can Google TGI Gunaco Playground. There you find on Hugging Face demo that you can use. And that's basically what I have. So we learn about quantization, how to deal with outliers, and then K-bit inference scaling laws and why 4-bit seems to be best. And then we talked about QLoRA, how we can make the memory of the fine-tuning 17 times more memory efficient, but preserve the 16-bit performance through this information theoretically optimal data type. And yeah, so with this, you get like very, very cheap evaluations, fine-tuning. And so it's very cheap now to develop chatbots and other models if you want to fine-tune them. And that's what I have. Thank you so much.
Awesome. Thank you so much for a very interesting talk. We have a ton of questions from the audience and from ourselves. So yeah, we'll jump in. So I think we have around 15 minutes and go from there. So just to start off, one thing we were pretty curious about is with QLoRA, obviously drastically improves efficiency and increases accessibility. What are some of the differences in quality that you notice versus like full fine tuning? And what is some of the intuition around what the parameter efficient fine tuning techniques offer versus what you could still get via full fine tuning, if there are any like major categories there? And on a similar note, I guess some prior work from a few years ago at this point, I think Ethan Perez, like true few-shot learning, studies some of the earlier parameter efficient fine-tuning methods and finds that a lot of hyperparameter tuning is required to get high quality in some cases. And so like, what are some of the protocols here to do this evaluation, and how sensitive do you see these techniques to those kinds of decisions?
Yep. Those were a lot of questions, but let me try to get through it like one by one. So the first was, what is sort of the qualitative difference between 16-bit models and 4-bit models with QLoRA if you fine-tune them? And so there, if we just look at benchmarks, the numbers look very similar, and we see very little difference. There are some tasks where it seems that 4-bit models have a bit more difficulties. And how to think about it, a common pattern that I'm seeing is that, so you can think about each word generated depends on all previous words. And with quantization, the distribution of probabilities can sometimes be a little bit funky. And you might generate a word that is sort of very uncommon, and then the language model gets confused, and then you can generate gibberish. And that doesn't happen that often, but with quantized models, it can happen. And so if you want to really prevent this, you need to be as close to 16-bit as possible. It's one of these things that happens rarely, but you never have guarantees when you generate, and so that is a problem. That's why we need sort of very high quality quantization, and we have some follow-up work where we basically SPQR, where we basically quantize. We solve this problem by quantizing with sort of very high precision, and then the generations are basically the same. And so, yeah, that's one consideration. Then the next question was, I mean, there were a couple of questions. Maybe Ken repeat the next question.
Right. Just that makes a lot of sense. And just the last piece was around sort of the hyperparameter tuning and sensitivity to some of the protocols for training QLoRA.
Yeah. So there are a couple of things. So one thing that we noticed is if you have low rank adapters, the common protocol was actually very suboptimal. So we spent quite some time to generate very high quality baselines for 16-bit. And to compare it with our 4-bit models. So if you have the right hyperparameters, it is very stable, but we needed to change these hyperparameters to find the stable configuration. Once you have these configurations, they are very stable for 16-bit and for 4-bit. You basically don't need to change anything. The other thing is a question of how do you evaluate few shot learning? Parameter efficient fine tuning if in the setting where you do few-shot learning. And so what we find there is that if you have very powerful foundation models, then it becomes less and less important. Sort of, it's very, very difficult to overfit. So there are not so many academic examples of this, but in the open source community, some people just fine tune on 20 samples. They do it for multiple epochs. Then their loss curves look like crazy. They overfit like crazy. But then if you try the model, it feels very general. So something funky is going on there. We can't really see it in our sort of data that we gather, but the models seem to just work and just generalize, which is very curious. The other thing that might be sort of responsible for that is if you fine tune the entire model, you fine tune quicker because you adjust all the weights. But a big problem is you also change the existing features. And so you use general features. If you have QLoRA, you freeze the main model, and these features will basically stay the same. So you learn some new things on top of the old model, but you mostly can preserve the generalization performance of the old model. I've been told, particularly in protein folding, if you look at the some models there, that's actually very important. QLoRA is actually better than fine-tuning in terms of generalization because you have this regularization effect. And so, yeah.
Thanks so much, Tim. This was a really great talk, really great to hear kind of about this from, a paper in 2015 that kind of started all of this. Not super common that you see that these days. One kind of, I guess, category of questions that we're getting a lot in the chat and that I was kind of curious about as well is what kind of hardware support do you need to support these new floating point types? So obviously you're not going to have like a tensor core that can do these things, but how does that affect, how you design the floating point types, the end-to-end training speed, and kind of all these questions?
Yeah, and that was actually a long-standing problem for me. Like, if you so first of all, the custom data types that are designed are not supported by the GPU. So there's this distinction between a storage data type and a computation data type. You always need to convert to the computation data type to do a matrix multiplication or some kind of operation. And so basically this conversion often happens in cache. That means you load 4-bit values in the custom data type, and then in cache you do a quick sort of dequantization to the computation data type, which is usually 16-bit. And so the main problem with that uses quite a bit of instructions. And often if you talk about deep learning software, you think about, are you flops bound? Are you memory bandwidth bound? And actually with these kinds of kernels that I write, they're often instruction bound. So it cannot execute, the GPU cannot execute enough instructions to do this conversion. But yeah, over the years, I have figured out a couple of things that are sort of a bit more general, where you can actually save instructions and have pretty good speed ups. So for 4-bit inference on consumer GPUs, you can get up to 3.8 speed up. And so that's close to the 4.0, that is sort of the theoretical limit. And so that just works really well, but it's a little bit tricky. So I have code for CUDA, but if you now want to transfer to some different software, let's say, for example, Apple Silicon, you need to figure these things out because it differs a little bit between hardware.
Cool, great. Yeah, that also answers, I think there are also some questions about, other hardware platforms and things. So really great there. Another kind of set of questions that we're getting is wondering about the outliers. So these outliers seem really interesting. They seem really important. I guess, do you have any kind of intuition about sort of what they're doing, maybe from a mechanistic level, and kind of how common are the outliers? Are they like one weight every layer, or like there's outliers just kind of everywhere?
So I have a paper about this LLM and date. And so I also did like follow-up research. I haven't published this yet, but I've seen already some papers that exploit similar artifacts. So the outliers, about 0.1% of the neural network will have these outliers. They're highly systematic in large foundation models. And so just looking at the weights, you can see like, oh, there's an outlier, there's an outlier. And so the function of these is they seem to act as a conditional memory. So if you look at the largest values of these outliers, they usually occur in the beginning of sequence token. And they are there because that's the only place in the neural network which is completely independent from the context. And so the neural network stores some information there to then be reused in attention lattice layer. So for example, if you want to carry a sum in an addition, then it would store the carry there to do the addition on the next layer. And that's sort of what I've seen in some follow-up work. And that's how you can think about it. There's a paper that sort of calls these dimension registers, and it adds special tokens to add more registers to the neural network. And with that, you can basically store more of this conditional information in more spaces. And that works quite well. And so, yeah, there's more to these outliers. I could talk for 15 minutes, probably just about these outliers, but it's very interesting. It's very systematic, and they have a special function, very structured information in the neural network.
Thank you. Yeah. And one other set of questions was about the dynamic exponent quantization. And so you talked about how at runtime, you're kind of making this decision about whether how many bits to allocate to the exponent versus the fraction. So some questions were around how we can decide this allocation and what that mechanism looks like. And looking more at the result plots on accuracy. So one of the student questions was, what might be the reason for sudden downticks of the dynamic exponent integer accuracies towards the end of those plots?
Yeah, let me go back to the slides. So if we go to the dynamic exponent quantization, yeah, again, so sort of there's this indicator bit, and that determines the number of exponent and fraction bits. And so if you implement it and want to implement it in a smart way, it's actually slower than implementing it in a dumb way, how to decide this on the GPU. And so how you implement it in the GPU is just binary search. You basically search all the possibilities and get closer and closer to the value that is closer to a particular value with a particular index and exponent and fraction. So again, here, a binary search through all possible values is the fastest way to implement it on a GPU. Then the other thing, let's see if I have a slide on this. I don't think I have it on this slide deck, but the question was like, we saw these downticks in the 3-bit quantization. What is this? And so these are instabilities. And these are actually also related to the outliers that I talked about. before. And we have a paper, it's the same paper I talked already about, the SPQR, that does sort of a detailed analysis on these outliers and how they affect quantization. And so if you fix them up just the right way, you can actually make 3-bit quantization work better than 4-bit quantization. And so again, outliers are the key here. It's a bit more complicated than just looking at a couple of dimensions. It's very complicated patterns. But so if you don't take care of the outliers, you see similar things like here, the performance basically goes to random performance. And if you prevent this and quantize the outliers separately, you can actually increase the information density a lot. And it's quite a bit of key to improve quantization techniques.
Awesome, thank you. Yeah, that makes a lot of sense. And one other question was around whether quantization can be used when training the base model to start with, and what are some of the challenges that you've experienced in your research when applying quantization during training, and some tricks for instability and so on.
Yeah. So I did have like 2 papers that do 8-bit training, one on large language models and one for clip training. These are all a little bit different, but sort of the main problems, also in the literature, there's a couple of papers that pre-train in 8-bit. And again, the main challenge is sort of these outliers. But the interesting thing is these outliers do not exist in the beginning. They just very slowly emerge during training. And so the challenge is to handle these outliers in a way that it doesn't affect training, but at the same time sort of maintain them or give the network the ability to do the information processing that are normally that makes normally or has the requirement of these outliers. And so one simple trick that's actually used in computer vision quite a lot, not in large language models, is layer scale. And that just scales the outputs of a transformer block by a scalar, and the scalars learn. And if you do this, the neural network can sort of very easily scale the outliers to a certain dimension to have a certain effect. But at the same time, what we see is that the overall size of the outliers is much more confined. So usually outliers can be super large compared to the other values. But now we have a much smaller range, and that makes the quantization error lower. Beyond this, there are a couple of other artifacts. You need to fix some things in the optimizer to get a low-bit precision training working. And yeah, some other more specific things about logits and what scale they take. But if you have the right recipes, you can make it work. Currently, it's not super standard, but floating point 8 training, I think in industry, or probably most companies are already doing it. And they're not publishing their code because it's sort of competitive advantage. But we also see soon probably papers and work on that in academia, and most people will switch to floating point 8 training. Int8 training is also possible, a little more difficult, but you can figure it out. And I think that's sort of the landscape at the moment.
Cool. Yeah, that's really interesting. Like kind of watching it all evolve. I still remember when, Susan's talk, a couple a year ago where FP16 was, and now we're down to FP8 is pretty crazy. So I think the audience also kind of really liked your discussion about the data sets at the end there. We had one question about, so another very popular use case is kind of code generation, tool manipulation, things like that. They're just wondering, have you looked into kind of fine-tuning data sets for that, or even, how do you even evaluate those? What are relevant kind of evaluation benchmarks for other very popular tasks like that?
Yeah, I think with code generation, it gets a little bit more complicated. So from my understanding, if you do code generation, there's one good performance on the benchmark. The other is actually user experience if you want to use these tools. And you also see this sort of divide with other instruction fine-tuning. So the data sets that we use, they're sort of more studied in academia. But if you look at all the open source instruction fine-tuning data sets, sort of they're very specific, but very high quality, very good performance, and you have a much more general chatbot that works much better. And so there is this sort of this divide, and it's mostly like what the open source community is doing is they taking a raw data set, trying it, getting some results, looking at the model, testing the model, and then they feel like, okay, this is like this. Add a couple of examples here, have specific procedures. One procedure that's very powerful is like this open ORCA data set procedure, where you take existing instruction and improve them. But the overall process is really to take a data set, improve it a little bit, train again, test again, and take the data set, improve it a little bit, and go through this loop many times until you get very high quality results. And the important thing is really to use a model like you would use it yourself. Academic benchmarks and general benchmarks, they often don't capture it, they capture a portion of it. But if you want to really a model that is used by people, then you need to have this iterative approach. And so that's quite a divide between academia and how it is in practice. The same you will see with code models, particularly with code models, because you use them in a particular way. And it's important to consider that, how they are used.
Well, thank you. And last question before we sign off is just on a closing note, what do you see as sort of the big remaining directions for improving foundation model accessibility and efficiency? What are you excited about in the future?
Yes, so in terms of accessibility, we are pretty good. I was working on one technique and I was already thinking like, is this worth it? Like, it's already so accessible. I think there are a couple of more innovations and the models still get a little bit larger. I was working on one thing for the 180 billion Falcon model that does this sort of some swapping between the CPU and GPU to make it sort of very high efficiency that you get maximum throughput on a single GPU. But I think right now the big challenges are mostly using these models, and we see that we go from 4-bit to 3-bit, but then the challenge becomes that most 3-bit techniques, they have very complicated computational patterns that are very inefficient on hardware. And so this is also sort of a frontier that's important for mobile devices. So often we now have pretty high quality models that are 7 billion. But if you want to run something on an iPhone for all the apps that you have, then I was told like what would be a target is a model that's only 2 gigabytes in size. And if you do the math, we are not there yet. We need to be smaller. And then what I also said is we need to develop techniques that are both precise at 3 bits, but then also are efficient to use. Because if you have super low compression, but it's so difficult to use, then it's a bad trade-off. And so, yeah, I think that's sort of the frontier right now.
Exciting. Thank you so much. And this was an amazing talk and really, really great and interesting work. Thank you to everyone for coming and watching the talk as well in the audience. And you can check out prior talks and future talks on the website, as well as subscribe to the mailing list at mlsys.stanford.edu. Next week, we're super excited to have Deepak Narayanan talk about parallelism. Yeah, thank you again, Tim. And
we'll wave goodbye.
Thank you so much.
And stalling until, okay, there we go.